All right, so our next thing we're going to do is the piroxicam concentration. So the table here gives an estimated concentration in micrograms per mil of the drug piroxicam taken in 20 milligram doses once a day. Now we need to find the log model for the data. Then we express the end behavior of the model by using limits, estimate the concentration after 2 days of the drugs being into the body. And then after that, even though we don't have this stated, let's also go ahead and find the inverse, okay? So first thing, we need to find the log model. So let's go here. And our log model is going to be in the calculator. And again, what I'm going to do is I've already typed in the data, so we don't have to worry about that. And all we have to actually do is I'll show you we have the data here though. You know, we have 1, 2, 3, 1, 3, 5, 7, and then all the numbers like that. And we're just going to do a log plot or log regression. Well, better use L1, L2. And so this is going to be our value for our log plot. So let's write this down. And so this is going to be part A. So A is going to be, now we're having C of D, I think is what I'll use for my function. And the log model we had was 1.182 plus 2.216 ln of D, because we're using D here. And our units are going to be micrograms per milliliter. And after of the drug, I guess, of piroxicam after X day or D days. Okay. All right, so that's our log model. So we understand that one. Now we express the end behavior of the model by using limits. Well, as we have one day, it goes up and it keeps going up. And if we remember how log plots work, they're just going to keep going and going and going. And so for B, what we're going to say is the limit of our C of D as x goes to infinity is going to be infinity, because as we keep going this way, it's going to keep increasing. And so it's just going to keep going up and up and up. Okay. Well, we can also think about, well, what if we go the other direction? Because we do have going the opposite direction. We can say the limit as x approaches 0 from the right for C of D is going to be equal to, well, now that's, remember, it's going to go down, down, down. So it's going to go to negative infinity. So that's the end behavior for both sides of our graph, okay, or the model. Now, if we want to estimate the concentration of the drug after 2 days, well, we're going to say C of 2. Now, this time we didn't do any aligning, so we don't have to worry about that one. And so it's going to be 1.182 plus 2.216 ln of 2. So let's look on our calculator. And so we had the 1.182 plus 2.216 ln of 2, and we get 2.718, and so that was going to be our micrograms. So this is approximately 2.718 micrograms per milliliter for the concentration in the blood after 2 days, okay? And now, like I said, it doesn't say so, but let's do part D and do the inverse. Okay, so now we're going to find D of C. All right, well, remember the inverse of a log is exponent. And so what we're going to do is we're going to use our same data. We're just going to go over here, do a 0, which is exponential. Now we have to swap our X and Y list. And so this is now our new value that we're looking for. So this is our inverse, okay? So let me write this down. So if we go back over, this is going to be 0.6 1.603, 1.562, and we're raising it to the power c. And this is going to be days, okay, because that's our unit here. So that's going to be days needed to reach a certain concentration. And it's going to be C is going to be less than or equal to 7.5 and greater than or equal to 1.5. So somewhere in that range, that is the model that will actually work, okay? And we won't actually plug a value in this time. You just plug that in and take 1.562 raised to that power times 0.603, and you're going to get the days. And hopefully, again, check it, make it line up, see if it works, okay? So maybe you want to do 6, and you want to see where it is. And it should be between 7 and 9 when you get done, okay? All right, logarithmic functions are either increasing or decreasing, as we've seen. So for any possible input value, there can be no repeated output values. So it has to be one-to-one, basically, is what we're saying. So this means we have the inverse function associated with, which is what we've been looking at. Now, the inverse function for log, as we've said, is the exponential function. And these are kind of some general relationships here below that model between the log and the exponential. So, if we have f of x equals a plus b ln of x for b not equal to 0, then the inverse is going to be something a bx, okay? And where a is going to be e to the negative a over b, these a and b's, and b is going to be e to the 1 over b, okay? Now, if we start off with a bx like this, so the kind of the inverse to start with, the inverse of that, again, with all of our conditions here, then it's going to be a plus b ln x, where a is going to be now ln of a, negative ln of a over ln of b, and capital B is 1 over ln of little b. Okay, and so those are how it is. But we're plugging these directly into our calculator, swapping the columns, changing it from an exponential to a logarithmic or vice versa, and we're getting out our relationships quite nicely, and it's not too bad there. So that's going to be kind of the key thing, is how it works is, we can use all this here, or we can use our calculator to actually get us the values. All right, so let's look at this one, cable subscribers. All right, so what we have is basically some kind of a function, S of R equals 89.391 minus 6.486 ln of R. So we have this function, and it says the number of cable subscribers in the US as a function of the average monthly basic cable rate can be modeled by that. So our R is a cable rate, and then S is the number of subscribers in millions. And what we want to do is we want to use the model to estimate the number of subscribers in millions for the following monthly basic cable rates, 34, 38, 42. All right. So we're going to do that. And then we're going to exchange the input and output values for the 3 points found here, and then find the inverse function with R with input S unit. So it's going to be, we're going to find some R of S, and here we're finding the S of R. Okay. And so what I'm going to do is, this is the model, but I'm going to actually type it in like we're actually looking for the model. And then I'm going to do the calculation to show that it does get the model out. And then we're going to do the inverse of that model to actually get to that point. So I'm going to go to the calculator now. Now this one I don't have because I haven't actually stopped the video yet. So let's clear that. Let's clear that. So now we know we're going to have a rate of 34, we're going to have a rate of 38, and we're going to have a rate of $42. And now we want to find the subscribers. So that's going to be our L2. So now we're going to take our equation, 89.391 minus 6.486 ln of 34. Okay, and if we hit enter, it does that calculation for us. Now, if we go back up, guess what? We just see the number. We don't actually see the equation. And so we just have to retype the whole equation in and say, okay, well, this is going to be 89.391 minus 6.486 ln of now 38. And we go down, which is what we expect. And then we have our, again, 89.391 minus, and then we have the 0.486 ln of 42. And so now we have our third point, okay? All right, so let's go show that that ln is what it comes out of. So we'll do a 9. Now we have to go back and remember to put that as L1. That's going to be our L2. And guess what? 89.391 and negative 6.486, which is, if we go back to our thing, exactly what we have here, okay? Now what we want to do, and so we've done the initial thing, and so what we can do is we can write our numbers down here because that's the values we're going to get. That's the number of subscribers, and so what we can do is we can take those numbers, and that's what we're going to write into our table. Well, I'll write those down and then we'll put it in our table a little bit, but now what we're going to do is we're going to do our inverse function. So this is the log as it is, so we're going to do the inverse, and so that's this exponential. And remember, we swap those out because they're not going to be the same way. And so the inverse of that function they gave us in the book is this: 96718.6.056, and then 0.857 and to the x, okay? And so let's go ahead and write down what we have. So, all right, so our first one, we had our table and we had, let's see, the rates, and we had the subscribers in millions. And so the rate was 34, and these are dollars. So 34, 38, and 42. And we found that this one was 66.519. This was 65.798. And this one was 65.148. Okay. And so that's the table, to estimate the subscribers in millions. Then when we did our exchange, we actually said, okay, this is the X's and these are the Y's now. Then we found R of S because we were kind of basically doing the inverse. And we said that was actually 967,186.056 times 0.857 to the S. And this is going to be in dollars. Okay. Now, what do we know about this? It's going to be between those number of subscribers. So that's going to be where it's going to be from. It's going to be, from 65.148 million subscribers up to 66.519 million subscribers. Our rates are going to come out somewhere in there using our function here. Okay. And so that's how we would do that one. Again, we used our calculator, the table itself, to get those values. Now, we can't go back and see those equations, but we can actually see the numbers here. So that's kind of a nice thing. And then we can, after that, just use our thing. So we don't actually have to write something down and only put 3 decimal places in here. When we do that calculation, we use that whole equation, and so we get all these numbers. And so it's a little more accurate doing it that way, I think. So that's kind of how I would suggest doing it. All right, so we'll pause there and we'll come back in a little bit.